Okay. Hello, everyone. Welcome to another episode of our Vanderbilt Machine Learning Seminar. Today, we are excited to host Jiajun Wu. Jiajun is an assistant professor of computer science and psychology at Stanford University, working on computer vision, machine learning, and computational cognitive science. Before joining Stanford, he was a visiting faculty researcher at Google Research. He received his PhD in electrical engineering and computer science from MIT. Jiajun's research has been recognized through uh, many awards, including a Young Investigator Program by ONR and by AFOSR, the NSF Career Award, the Okawa Research Grant, Paper Awards, and his work has been finalist at ICCV, CVPR, SIGGRAPHs Asia, and so on. And he has received the dissertation award from ACM, AAAI, and MIT, and also the 2020 Samsung AI Researcher of the Year and Faculty Research Award from JP Morgan, Samsung, Amazon, and Meta. And the list just goes on. We are very excited to host him today. And Jiajun, with that, the stage is yours.
Okay, yeah. Thanks, Sahel, for the introduction, and thanks for having me. I thought this thing is really well organized because the organizers like Hui really was very considerate and also had a lot of everything's so well prepared and organized. So I really appreciate it. And hopefully in the future we can visit in person. But okay, so let's get started. So I'm going to talk about because I thought this is the machine learning series. I usually give talks that are more on the vision side. This is still about computer vision, but I thought there might be a bit more of a learning component or machine learning component that could be interesting to the machine learning community at Vanderbilt. Okay, so I'm going to talk about concept learning across domains and modalities. So like how can we really model a concept, right? And in the particular context here, we want to understand and model mostly like visual concepts. But still, the visual concepts can come from data in different domains and can come from different data in different modalities, right? It can be 2D images, it can be 3D shapes, it can be, even not like beyond perception, it can be like interactive in the sense that they're like, let's say actions by robots, right? So how can we model concepts from all these different modalities in these different domains? And in a transferable way, but also, of course, the thing may sound like concept may sound a little symbolic. And the work I'm going to talk about is indeed a bit symbolic. But of course, in this age, you also want to think about how we can integrate these concept learning, maybe even a more or less symbolic framework with all these foundation models, which has shown to be really powerful, right? So, okay, so that's the theme of the talk. Okay, let's get started. So concepts play a lot of role in scene understanding, right? And if I show you a picture like this and realize, okay, I can ask you things like what's the color of the fire hydrant, and you answer that by yellow because you recognize there's a fire hydrant and you can try to infer its color. And if I ask you how many zebras are there, you can find the zebras and say, okay, there are three of them, right? So it has a lot of applications. And if we go to like simpler cases, like, this is just a really simple example from the Clever data set a few years back. Then, realize there's a green cube made of metal, there's a red sphere made of rubber, and you can use concepts to do a lot of things like question answering. What's the shape of a red object? Okay, you can find the red object and inquire its shape, and the answer is a sphere. You can do image capturing, like there's a green cube behind a red sphere, and you can do retrievals like rubber sphere, right? So of course, these days, we can do a lot of these things with GPT-4, but, I think the task here and the notion of concepts is still really important because, if you tell GPT to generate, let's say, I think, if you have GPT right now, you can test it. You can say, let's say, generate three spheres generate an image of three rows of spheres where they were like the first row has three spheres, the second row has five, and the third row has like nine. Would it work? I think in most cases it probably won't work. So I think that still shows like the notion of individual objects and individual concepts might be useful even in this modern context. Okay, so many years ago, like when the data set was originally proposed, we actually tried this kind of pretty simple, really simple approach to do more like a reverse engineering. And, so we first parse the scene to solve the problem of, visual question answering and Clever. We first parse the scene into individual objects. Like the first object is a red cube made of sphere, a green cube made of metal, and the second is a red sphere made of rubber. And you infer the scene into these object-centric representations and their attributes. And then you also parse the language into, using semantic parser to get a semantic program of the of the language that say, okay, what's the shape of a red object means I want to find something that is red and then I want to carry its shape. And after that, you don't even need the input image or language, right? Now you can do even a purely symbolic execution or reasoning using your inferred program representations and scene representations by just, query the right object, finding the right object and query its shape. And the answer will be sphere. So this kind of purely, of course, the scene parsing and semantic parsing are done by neural networks. But then after that, everything is like pretty rigidly symbolic. And you may have already thought, okay, this is really restricted, which I agree in many ways. I'm going to talk about very soon how we have improved it. But sometimes if you look at what's the good thing about this approach is it is restricted, but it's really data efficient, right? So if it requires only if you train on 1% of the data, like training questions, right? And then you can see that already achieves a very good accuracy. It's only a small performance degrade compared with if you train on 10% or 100%, while the new end-to-end neural networks are performing much worse. So there's this question about how you can really leverage have data efficiency, and so and if we have some of these kind of the notion of concepts and turn out to be really efficient for really improve the data efficiency of your models, which is very useful in many different ways. So this sort of motivates us to keep exploring this approach. And of course, if you want to go from these simple domains like clever synthetic domains to real world, then now there's a question that is, how can you train a scene parser, which requires the concept annotations, and how can you train the semantic parsing, which requires the program annotations? Right. So in real world, here's a picture of horses grazing, and now the question is, are animals grazing? How can you get the concept annotations or the program annotations? That seems very unclear. So okay, now this is a little bit 2017 or 18 is considered ancient by today's standard. So let's look at a bit more of a more recent approach, right? So I'll say to solve this problem using a modern approach, then the modern approach will be okay. I can use some kind of the semantic parser. Why now you can just use like Codex or GPT-4. I think Codex has retired, so now it's all like GPT-4 and 4.0 and 0.1. So you can get a program, and then you can now execute a program. But instead of executing it symbolically on a symbolic scene representation, you can execute it using pre-trained vision language models, right? You can say, okay, animals grazing means finding animals and query if they're grazing. But how can I find animals, or how can I query if they're grazing? I just send it to a vision language models, right? Which has, and it can be like large vision language models, or it can be more, if you look at these kind of pretty popular approaches in computer vision, like Viper GPT and visual programming. And visual programming actually, I think, won Best Paper Award at CVPR 2023. And what they did is, they actually execute these programs step by step. And every step you call, for example, finding animals, that means I want to call a pre-trained object detector and try to locate animals from the images. Okay, so this is kind of this modern approach, right? In that sense, I have pre-trained networks for executing, for extracting the programs and for executing programs. And the approach is great, and then it's pretty general. Right now, it works on general images. And there are mistakes, but you can say with O1 or stuff like that, the programs are getting more accurate, and hopefully the execution modules also get more accurate. But still, there's one issue, right? The one issue here is the method is like inference only, right? So everything here is kind of now pre-trained in this modern context because, yeah, the GPT-4 and VLMs are all like pre-trained. And is that possible for us to not having a purely pre-trained approach, right? Because what if I go to, again, let's say I want to do concept learning across domains, across modalities. What if I go to a new domain, right? What if I have data from a different modality? Then I may not have these pre-trained models, right? Let's say, I may have a very good pre-trained models on 2D images. But if I go to 3D shapes, I have much less good pre-trained models because there are just not that many 3D data. If I go to human motions, or if I go to, robot actions, then there's just like much fewer data, right? So now the question is, if I rely on these kind of purely pre-trained models, then, when the test data is from a different domain, they just can't do it, right? So it would be nice if we can have some ideas about how we can not only use these pre-trained models, but also think about ways of, fine-tuning them at least, or even like do some kind of joint training. Okay, so I'm going to talk about how we are able to actually do some kind of, can say fine-tuning or joint training. But the work is fairly recent because we built on top of these foundation models. But the idea was kind of a little old now, but it was a revival of the old idea. But I thought the old idea was still very interesting. That's why we revived it. right? So the idea is, it's possible for us to do some kind of joint learning of concepts and programs, or you can say semantic parsing. Just try to understand at the same time what are the meaning of the concepts like words and object, visual concepts, but also at the same time learning to learn the meaning of the language so that you can do parsing. So really, because you don't have annotations on either concepts or programs on natural images and natural language, now the idea is you have the learning of each bootstrap the other. So concept learning and program learning really help each other. And I'm going to talk about, okay, let me give you first a specific example about what that means. Let's go back to this simpler example, right? There's two objects, and the question is, what's the shape of red object? And here, what are the concepts? There are two categories of concepts. The first one is you first do object detection, then you extract, visual representations for the objects. So these are like the visual concepts for individual objects. And at the same time, you can parse the sentence into a program, but without assuming you already understand, what is red and what is shape. You also assume, red are things like, these words are the concepts embeddings, right? So then you can put together the whole framework in this, you can put together the concepts and programs into a neuro-symbolic reasoning framework, which I'm going to introduce later. And as showing this, our, kind of old work now, 2019, on neuro-symbolic concept learner, and it'll output the answer that is sphere. But before I talk about it, right? So what are the concepts? The concepts here, there are two kind of concepts. There's visual concepts, embeddings for objects. There are word concepts, right? So the embeddings for the words. And, of course, all these things can be now sort of pre-trained. You can use some pre-trained embeddings and whatever. But now the question is it possible for us to still learn it or update them or at least fine-tune them, if we want to move to a new domain, right? And the program is, just the form, the semantic form of the question. Okay, as I said, the concept learning and programming were really, could help each other. And in this paper back in 2019, we actually did explore both. But today I'm going to only talk about one of them, which is how program learning can help concept learning, because, the structured, parsing now, especially if you have O1 and stuff like that, it seems pretty good. And it seems much harder for concept learning to help the other way. But, that also requires much larger scale training, which we couldn't explore. Back then we explored a little bit at a much smaller scale. So I'm going to talk about this one direction, the program learning help concept learning, which is still very relevant even with all these foundation models, and we did revive it with the foundation models. So how we did it back then in 2019. So if we already assume we have the program form, which means what's the shape of a red object, I already know it means I want to find something that is red, whatever it means, and I want to query its shape. So now, how can I use this form to help my learning of the visual concepts and the word concepts? Okay, so what I can do is, I can take this object embeddings, and then I know, I want to find something that is red. I can send it to this kind of small neural network, like think about it as a modular neural network. And then you can transform the embeddings from the object one to, let's say, another embedding, which hopefully is the color of object one. You can do that for the second object, and then you can compare them with the embedding of the word red. You realize, okay, the color of object one is pretty far from red, and color of object two is much closer to red. Okay, so now going down to the second object, and going on to the second step, now you realize, okay, object two is more likely to be red. You can send it to another small neural network, in which the goal is, hopefully output an embedding for the shape of the object too. And in practice, these are not like individual neural network. They can be just one neural network, but with just different conditioning. And okay, so you get another embedding, which hopefully captures the shape of object two. You can compare that with the cube, which is, a word of shape, and spheres and cylinders. And you realize the shape of object two is pretty different from a cube, and much more close to being a sphere, and also pretty far from being a cylinder. Right, so this gives you an answer that is, okay, the color of a red object, the shape of a red object is a sphere. Okay, and all these kind of forward steps, execution, you can be, first they're like individual modular neural networks, and even the logical operators can be approximated to differentially also using neural networks. So the whole forward process, the execution process of executing a program using these embeddings are, fully differentiable, right? So, and you may say, okay, originally maybe my embeddings are not very accurate, so there's no guarantee that the execution will be correct, which is right, but you still will get an answer, and you can compare your answer with the annotations, right? What are the annotations in the VQA setup? Is you have the questions, the images, and the answer, right? So you can compare your answer with the ground truth answer, and that gives you a very weak supervision. But that very weak supervision, as I said, because the whole forward process is end-to-end differentiable, you can do backpropagation, and you can update now the embeddings for both the visual concepts of the objects as well as the concepts of the words. So this allows you, to leverage this already, understood concepts to, understood programs to help you to update and learn better concepts. And so think about it, right? If you contrast this framework with things like GPT or visual programming, then they get a program and they just execute it. But here, in addition to just executing a program, you are actually also comparing the output of a program, the output of execution and output of a program with a ground truth answer. This allows you to better understand and update the visual concepts or embeddings for both the words. And you don't have to update both, right? If you have, let's say, if you have a very good embedding model and you say, I already have a perfect understanding of words, then I don't have to update it, right? No, all you can do is to update, let's say, the visual representations, especially, let's say, if the input is no longer an image. What if it's 3D model or 3D point clouds? Or human motion data, right? So this allows you to really adapt, your pre-trained models if you have any, or just like any models that has not been trained from scratch to learn representations for these visual concepts. Okay, so this is how program learning may help concept learning. As I said, concept learning can also help program learning, as we did in this 2019 paper, but I'm not going to talk about it here because it's just a bit less relevant in today's context. Okay, so before I talk about how we revived it, let me first show some the results. That's 2019 results, still kind of impressive. And this is done by Jiajun, who is back then she's an undergrad and visiting MIT, and I was still a grad student at MIT, and now she's a final year PhD student at MIT and graduating on the job market. Okay, so what's good about this 2019 approach back then? First it's still very accurate, right? It still achieves almost perfect results on Clever. That's not too impressive though, because everyone's like doing perfectly on Clever. But again, similarly, it is also data efficient, right? Just like the best of the symbolic approaches, they're like, oh, they're really data efficient. You only need like 1% or 10% of the data. And here, if you train on 10% of the data, you still achieve very good accuracies, which are comparable to if you train on 100% and much higher than these end-to-end neural network baselines back then. And it supports combinatorial generalization in the sense that you can train on simpler images with fewer objects and simpler questions where everything is doing pretty well on the training set and or the test set of this scale. But if you test it on more complicated images and questions, the method still performs equally well, basically equally well, while the other methods has some, performance decrease. And because you no longer assume you're living in a world with 5 different shapes and 7 different colors and 8 different materials, you're instead learning the concepts for these, visual objects from natural pictures, and you can actually apply them in real world scenarios. As I showed in the very beginning, these are actual results in the sense that I can ask, what's the color of the fire hydrant? You can find the fire hydrant, you can create its color, and the answer will be yellow. Or how many zebras are there? You can find the zebras, you can count them, and the answer will be 3. And because the concepts are like, where I'm learning representations for individual concepts, I can also retrieve, other horses from the data sets, other people from the data sets, or I can retrieve compositional concepts. Like, can you find me more examples of person on a skateboard? Right. Okay. So we talked about this, neuro-symbolic concept learners. That was in 2019, and as I said, in the past few years, we have been first updating it, right, to incorporate more foundation models. For example, replacing the semantic parsers with GPT-4, actually first GPT codecs, and now maybe GPT-01. As well as updating the vision language models to use more updated recognition models. But the same concepts has been I think it persists, and we have been applying them also to different domains, right? Keep saying, okay, what if I want to learn it, apply it to different domains? So the domains we're looking into are their dynamic scenes, right? Instead of just reasoning on a static scene, what if I have a dynamic scene where there are objects interacting with each other? You can have more interesting reasoning. What about 3D scenes, right? Input is now 3D point clouds, and you can reason in the 3D space. What about 3D and dynamic in the sense that you can have human motion data, capture the human joints, and they move over time, and you can reason on that. And finally, robotic manipulation, where you have to learn not only visual concepts but also action concepts, which should be accompanied with the policy so that you can execute it. Okay, I'm gonna very, very quickly show like maybe one slide each on what we did in each of these domains, right? So for dynamic scenes, as if you look at this video, then you realize we can do a lot more interesting reasoning, including temporal reasoning. Okay, what shape is the second object that collides with the sign sitting there? Or causal reasoning in the sense that there are different types of questions that involve different levels of causal reasoning, such as explanatory. Okay, what objects are responsible for the second collision? Or what will happen next, predictive or counterfactual, what would have happened if the grid object were not there, right? So these kind of different types of reasoning. So we built a data set of it till 2020, has a lot of synthetic videos and 300,000 questions of all these different types. And I think right now it's still pretty widely used. And here, of course, in dynamic reasoning, it requires to understand dynamic concepts, not just like, okay, yellow object, blue spheres. Of course, you need that too. But to answer what will happen next, you need to, of course, do object grounding as we did before, finding the blue sphere and yellow objects. But now you also have to have event grounding. You have to understand what it means by a collision, right? So when it's a collide, what does that mean? You can do temporal grounding to identify collision. This will really help you to answer these questions. And for 3D, we also did similar things. That is, we can now replace the input. Instead of having an image as input, you can have 3D point clouds as input. Instead of having, image patch level encoders, you can have object-centric point cloud encoders, right? And you can have, binary, including object features, but also, sorry, unary, which includes object features, but also binary, which encodes relation features. And you can have, more modern semantic parsers like Codex or GPT-4o, which give you a functional program, and then you can do the similar thing as we did before. Now, instead of on image features, now 3D features, right? So, for example, it is not as simple as you may have thought, because in 3D there are additional things you have to consider, such as where you're standing, which direction you're facing, and camera parameters and stuff like that. But the high level concepts, the philosophies are really similar. Right. So here is an example. When I say facing the front of the shelf, right, you have to locate our shelf. You want to select the door that is on the right side of it, right? So, this means you want to first find a shelf, and you want to find a door, and then also the shelf, and then see if the door and shelf satisfy now a binary predicate, which is relate, right? So now you want to ensure that the door is on the right of the shelf. And so, it turned out, right, these kind of simple models also have very good data efficiency. And if you train on, 10% of the data, or even, I think this is 10%, this is 1%, you can see that the model still does. This is actually on the top, on the leftmost, maybe 0.1% actually. Anyway, so on 0.1% to 1% to 10%, you can see that our model has much higher data efficiency, especially, now you move to 3D and you have much fewer data. And you have some combinatorial generalization to novel pairs of objects and novel scenes and stuff like that. Now, compared with these are now all like end-to-end neural network baselines. This is 2023. So it's like just last year, and they're like, at least they were last year. You can see that having more like kind of symbolic or concept representations, but still, putting them into like end-to-end neural network, everything here, except for the first part where you expect program from the questions using Codex is, a separate part. Right after that, everything is like end-to-end differentiable, right? So still it is end-to-end differentiable. It just has slightly different inductive biases about objects and concepts in the neural networks, and which just directly give you much higher data efficiency and better generalization. And similarly in 3D human shapes, we did some kind of data set for 3D human modeling last year in ICML. I think I'm going to skip that, but you're welcome to look at our paper. And for robotic manipulation, let me talk a little bit about it. Okay. So similarly, we want to do this kind of primitive-based or concept-based robot manipulation. We want to learn policies that map from states and goals to the next actions, right? So here, let's say I want to pack the yellow flower into the brown box, or push the green blocks into the blue sphere. Then you realize, there are a lot of concepts here, right? There are things like green blocks, blue sphere, but also there are action concepts like pack and push. Here not only want to like ground them or identify them in video, oh, this is a push, but also I want to understand, like in dynamic reasoning, you have to understand there is a collide. And here now you say, okay, I have to understand there's a push. But you not only want to recognize a push, you also want to learn a policy that is accompanying the push, so that you can now tell the robot what to do, right? So the robot can execute a policy and say, okay, this is the push policy. And with, I can take parameters like green blocks and whatever, these are like target objects, but I want to execute the action. So You can compare our this kind of, you can argue as program-based modularity or concept-based modularity versus a simple pre-training fine-tuning approach, right? So in the simple pre-training fine-tuning paradigm, you have image encoder, you have a text encoder, you just send it directly to a control parameter decoder. And in our case, you have kind of a program parsing segment, and you want to understand, put the heart in the hole means I want to find something that is a heart, that is a hole, and then my goal is put the heart in the hole, but then I have a do operator, which is policy learning for the action put. And you can still execute the vision part more or less like programmatically as we showed before, but finally only for this do action, right, which you have to learn the control parameters, conditional action, and here the action is put. Okay, here's an example of execution trace, right? So here we have the, as we shown before, the disentangled modules for visual grounding and control parameter prediction. So we can parse the question again. Here in this case, pack the blue hexagon into the orange box means I want to find a blue hexagon, and I want to find an orange box. And finally, I want to the goal is put A into B, and I have an action parameter learning part, and I want to learn the action here is pack. So if I visualize the execution trace, you can see that the system is able to find the hexagon and also identify the blue one, and finding the boxes and identify the orange one, right? So now these kind of, the visual, the output of visual perception grounding modules are now sending as the input for the go module, which, try to, these are the parameters. Okay, A has to be in B, and send it to the action module so that it use reinforcement learning to learn the parameters about, okay, how I should move to pick and place so that I can put the blue hexagon into the orange box. So similarly, again, he keeps saying, okay, you want to do custom learning across domains, across modalities, because you want to have better generalization, right? It's like generalizing to different domains or data efficient generalization to different domains, different new scenarios, new combinations of objects, but also new tasks. And here, for robot learning, similarly, we have training examples about, you can say, pack the yellow flower into the brown box or push the green blocks into the blue sphere. You can zero-shot generalization to new objects like rain. I've never seen a rain. How can I know that? Here you're using like these kind of pre-trained vision language models, right, to identify objects. So even if you have now seen a rain during your training of the action policy, it is fine because the visual recognition part, it generalizes to recognize the rain. And now, so you should still be able to execute a policy even with the novel objects. And of course, novel compositional generalization in the sense that now you can push yellow flower into a blue square, which is a new combination of objects like target objects and target positions. But that should be no problem at all with this also a disentangled modularization.
Jiajun, may I ask a question?
Yes, I'm going to move on to the final part. So I think this is actually also a good place to ask like maybe one or two questions.
Fantastic. Yes. So, I mean, I love the idea. It's very reasonable. But one thing I didn't get when you were talking about the label efficiency, the data efficiency
Right.
of this model that's conditioned on the program, we see that as the data increases, the more data-driven models are performing better. Essentially, at the right end of the plot that you showed,
Here, yeah.
yes, yep. So the inductive bias is limiting the methods, right? It's helping when you don't have enough data, but it is kind of limiting when you have 10 to the order 100 train data, right? So, but why? It seems like here your model is actually generic. What is the limiting factor of this inductive bias? What is the inductive bias that's causing this behavior?
I would say, well, first, I think, yes, this is true. And second, I would say, yeah, I mean, this is kind of expected, because, if you have a lot of data, actually don't see a reason that you need to have like even more inductive biases, right? So I think the whole argument has been on like, okay, how can we generalize new domains in a very data efficient way? And what if the domain doesn't have that much data anyway? Right. So you may say, okay, what if I just collect data? But there are a lot of data domains that you actually, it's turned out to be really hard to collect any data. Like for example, what would be the physical properties of objects? And also in a lot of like science domains, it just seems very hard to get any data. So that would be the argument. Okay, so now going back to the third, at the third level, going back to your question about, if you do have a lot of data, right? So what's going to happen? Yeah, I think the performance are comparable, and there's no reason that our model should perform better, when you have a lot of data. And why is the case? First, I wouldn't say it's like really worse. I think it is like more or less like comparable because these are all like different types of, end-to-end neural networks, and we're like in the middle of them, right? So it's not like it is much worse. It is comparable. And what is, if you say, okay, why are we not performing the best? And what is, in some sense, the inductive bias maybe limiting them? I think that is actually a very good point because it is actually not even just in reasoning, right? I have like totally different line of work on like, I would say 3D reconstruction, inverse rendering, neural rendering. You have like instead of having a program like a program executor in the loop, you have like differentiable graphics simulators like renderers or physical simulators in the loop, right? You can think about at these differentiable simulators also as different types of programs. And here, the differentiable program executor is also a type of simulator. So they're all kind of similar, had the same kind of flavor. But I know we have been thinking a lot about this recently, and what's the reason that is, when you have a lot of data, yeah, sure, you're not expecting the model to perform like much better. But why is it mediocre? Why is not like at least comparable to the best one, right? At the top here, you know, I think it is also because whenever you have a executor, it can be a program executor, it can be some kind of simulator, it can be a renderer, it can be anything. It sort of assumes a domain, right? So any kind of simulator assumes a particular domain, and you want a domain assumption to be very minimal. But there are cases where you have still more or less some kind of assumptions on the domain. For example, a physical simulator may be particularly good at simulating rigid bodies. Or another simulator may be particularly good at simulating fluids, but not very good at rigid bodies, right? So in the case of our executor, you can think about it as, okay, you have these programs, but now you want to execute it to do object detection. But, it might be the case that there are objects like fluid, which is just not very good for detectors to detect, right? So they maybe detect something that is, it is not, so when you have a program executor there, you sort of are constrained by the implicit assumptions on maybe the domains or whatever of these modules. And here in this case, modules may be the performance of a detection algorithm or something. So I think then when you have a lot of data, and that will no longer be an issue for, I would say, a model with less inductive bias. And also when you have a lot of data, these kind of corner cases may appear in the test sets. So that is sort of limiting the system to be like at least at the very top, not at the very top. Does that answer your question?
Absolutely. And there are two related questions in the Q&A. Let me start with the second one. Is it possible that the efficiency is gained by the design of program, which having human efforts involved, and the data increase and the limitation of predefined program might be the bottleneck? So
Yeah.
essentially, like, is there a
So
way of learning that?
this is a great question, which I will just answer in the final part of the talk. So I'll skip that, and the last part of the talk is actually more about that. Yeah.
Fantastic.
And there's another one saying, I can read it. I'll just read it myself. It says, is there any general suggestion on how to derive the program or symbolic rules? Yeah, I think this is also something I'm going to, this is like at the end of the entire talk, I'm going to say a little bit about that. So I think, yes, I think this is good. So I think I'll just continue and then
Yes.
hopefully these questions get answered. If they don't, we can talk about it at the end. Yeah. Okay. Great. Is this the right section? Oh no, I think I skipped a little bit more. No, let me go back. Not this slide. This slide. Okay. So we have this kind of we have shown that this kind of concept-centric framework seems very good, and data efficiency, at least in domains where you don't have that many data, and we did show it on these different domains. Now the question is there anything that is still kind of left, right? So are we done, or can we still do even better? So when we ask the question about, what's left, right? Is there anything that's still left? It turned out that we find, the thing that is left could be actually just tied to even the specific word, like the left itself. Now here, for example, let's just look at the word left, right? So what's going on here is the same word actually appears in different domains, right? So if you look at 2D question answering, the question is there a red sphere to the left of the large sphere? Is there a dresser on the left of the cabinet? In temporal sequence reasoning, you have what part do they use before they move to the left? And in robotic manipulation, you have put T to the left of the white A. Okay, so here, what is here? Yes, these domains are so different. 2D images, 3D point clouds, human trajectories. Well, the language is the same, right? The same kind of language, just it's English. And same word, the same word left appears in different places. But what happens here, or what happens before is, we train these kind of different systems, different modules. No, they're kind of similar, but they're like still different systems on these different domains. And with, I think as one of the questions saying, oh yeah, maybe with slightly different programs or inductive biases more or less designed by humans, right? So how can we generalize? What if I go to a new domain and do I have to design new programs and all these kinds of things? I would say first, if you go to like domains with a lot of values, like human bodies or faces, you probably should, right? That's what people have been doing, right? You just have all these specialized models just for faces so that it looks perfectly realistic and you use it in games and movies. But, in general domains, yeah, maybe I don't have the capacity to design all these programs. And so it's maybe there's something that is shared, across all these domains. They're like domain agnostic or domain independent. And can we leverage that? And what would be that? What would that be? And it turns out, if you look at it a bit carefully, then yeah, it is the fact, and what is domain independent is the fact that you use the same language, use the same words across these different domains. So it is the same word of left. And so there must be something that is shared, right? Across these different domains. So if we look at it carefully, then we realize, and all these questions can be summarized into a domain independent reasoning module or independent reasoning, I would say, section. And here the query is, they're all in the form of, is there an object to the left of the target? And if I look at this question, then I realize, okay, what is going on here is they all can be parsed into similar programs. And what a program look like is you want to find object that is, there's a, I would say object, which is X, and there's a target object, which is Y. And you want to satisfy, right? You want to see if there's any object, if there exists any object X that satisfies this binary predicate of left, where, X is on basically the left of the target object Y. Right. So specifically, what is X, what is Y, as well as, how the binary predicate of left looks like, on these different features may vary, right? Because, what is a red sphere? If you give me an image or if you give me a bunch of 3D point clouds, then of course I need different kind of feature detectors to detect the red sphere. And then after detected, right, if the feature embeddings are learned from 2D images or from 3D point clouds, they're going to be different. So maybe the binary predicate of if A is if X is on the left of V, on the left of Y, also need to be, a bit domain specific. But the fact that there exists this kind of general program structure, there exists, the question always means if there exists an object X, which is on the left of target object Y, is domain independent, right? So the existence of these programs and the existence of these binary predicates are what is shared across these domains, and the meanings, the groundings of these, I would say individual objects, individual concepts, and even the binary concepts, binary predicates, the grounding are domain specific, right? So here, this is the domain independent reasoning part. And what is independent is the program structure itself. And what needs to be learned is, okay, how can I identify object X in these different input domains, and how can I learn if the encoded features of X and encoded features of Y are satisfying the binary predicate of left, so that X is on the left of Y. Right. So, here are some examples about, how can we go back to the original examples and ground this kind of program structure into these different domains. And in 2D, here the X is a radiant sphere of, it's a red sphere, and the Y is, a large sphere. And now the question is, if there exists X, which satisfy the predicates of of a radiant sphere, and also, another object Y that satisfy the predicates of large and sphere, and these two objects X and Y satisfies this binary predicate of left, right? So in this case, the answer is true. And that is similar for 3D. Here the target object is now a cabinet. The X object is a dresser, and you also want to do similar things about if they're, finding in testing if there exists an object X that satisfies the dresser predicate and another object Y that satisfies the cabinet predicate, and X and Y satisfy the left predicate. So I'm going to skip because they are like really similar for humans as well, for human motion understanding as well, and for robotic manipulation, except for at the end you have an execution parameter. Okay, so there are some things that are really shared across these domains, and the fact that it is these kind of logical forms, and all you need to learn is domain-independent groundings, right? So if the logical forms are shared, now this is sort of answering the second question. That is, oh, do we have to come up with new or different programs for different rules, different domains, or different programs or rules for different domains? The answer is probably not, because what is shared is these kind of logical structures across domains. So what we did in this work, that is we upgraded, you can see the neuro-symbolic concept into this what we call logic enhanced foundation models, right? So in our logic enhanced foundation models, we want to provide a unified framework for conceptual reasoning, learning and reasoning across all these different domains and tasks. And we have a domain independent reasoning module as an integration of a foundation model interpreter and a differential first order logic executor. And we have domain-specific grounding modules for each different modalities, right? So ideally, you have the same framework. You can train it on all these different domains. There's no change needed or minimal change needed, because you always need to have slightly different encoders, right? If you have 2D images and 3D point cloud, of course, you need a slightly different encoder. But you need very minimal changes across these different domains. And you can just train the single framework across these different domains and have hopefully compiling generalization to novel tasks. So this is what we did in this work published in last year's New Rips, called What's Left, and led by my, also Jiajun, who I shown earlier, but also my PhD student Joy Xu. So now the question is, if you say you have this domain-independent reasoning model, you still need to have a DSL for it, right? Even if you don't have to design a DSL, domain-specific language, for each domain, sounds like you need a DSL for, for your entire system, just one DSL for all. Then now the question is, what would be that DSL? Right? And as you may have seen here, I said a differentiable first order logic executor. So we are just very simply using, okay, there's no human design. We just take the most standard thing from a logic textbook, or it should be from an AI textbook too. But I think AI courses no longer teach logic anymore. I think we still do that at Stanford. There's like one lecture. But it is the most standard thing from a logic textbook, which is a first order logic. Right, so there's no human design, and it is just one framework taken from the textbook, and it's applicable to all the domains we have. That is the DSL, right? So we just use first order logic as our general, I would say domain specific. I would say the domain specific language DSL, yeah. And so then, we don't have to have any predefined DSL or programs for any of these domains, right? Just the first order logic, and that's it. And then we augment it with all these foundation models for execution. It can be pre-trained, it can be fine-tuned, they can be learned from scratch. So you can see all the logical operators here. There's iota, which means identify and stuff like that, and then there's not and or count, describe, which is like finding objects, and execute and do. Okay. So in logic enhanced foundation models here, also called left. So we have a domain-independent reasoning module, which is output by the DSL is just specified by the first order logic. And now you can have some prompting techniques so that you can have the LLM to output your program. So the query may be how many objects are left of the sphere, and the LLM may say, this program structure, which I explained before. And of course here, now you say the sphere, so now the predicate becomes the sphere. And you have a first order logic executor, which is again fully differentiable, right? Because you have to execute a program and you want it to be fully differentiable so that you can do end-to-end training or fine-tuning or stuff like that. So all the execution of the not and or operators, which are logical, are approximately differentiable, just like what we did 5 years ago in concept learning. It's the same thing. We just have neural networks approximate these logical operators so that they're all differentiable. These neural networks do not have learnable parameters. Okay, so maybe they're not saying neural network, you can say differentiable operations. But these are like executors, they're differentiable, but they don't have learnable parameters. You don't have to learn how to execute an or an. But what you need to do is you have to learn the concepts, right? And these are the domain-specific grounding model. You need to have, adapt these small neural networks, or, it can be large, conditional neural networks, but you can fine-tune them or whatever to learn specific concepts like, well, what does it mean by finding a sphere? And that would be different, of course, if the input is image versus if the input is a 3D point cloud. And what does it mean by if X and Y are, X is on the left of Y, so that they satisfy this binary predicate? Right. So the domain-specific grounding modules are, let's say we look at all these different domains we considered before: 2D images, 3D point clouds, human motion data, robotic action, robotic manipulation. then, for 2D images, you may have like a faster CNN. For 3D point cloud, you may have a point net. And for human motion, you may have a graph convolutional neural network or something. And, so you have these kind of different domain-specific grounding modules, and they may have different encoders, which can be pre-trained, but you can fine-tune them, or you can train them from scratch, which gives you the unary, binary, and ternary features, which has, one encodes like one objects or two objects or three objects, and give you the features. And then you can send them into the logical operators like and, or, count, and stuff like that, and give you the answer. Okay, so that is it. It may sound a little complicated. If you look at the code, it's really simple. I have one slide at the end to show how simple it is. But in terms of results, it is now one unified framework, one design DSL, actually not even design, one DSL, which is first order logic, and no additional design, no additional program or whatever for each of the domains. They're just one unified framework, and it has pretty effective concept learning across all these 4 different domains that we talked about before: 2D, 3D, temporal data, robotic manipulation. You can see that it performs pretty well, on all these different domains, right? So you can see it's comparable to M2M methods on all these different domains, and although they have different designs, and it is also comparable to the work that we showed before, right? On clever 2D reasoning, 3D reasoning, human post reasoning, and robotic manipulation. Now, these are kind of different specific modules that I talked about before. And, now I have this one framework for all situation, and it still gets pretty good performance. And similarly kept the data efficiency, which I'm not going to keep saying, but it is, if you train on 10% data, again, it is similar to the performance of these earlier neuro-symbolic framework. As we said, they're very data efficient if you train on 10%, or this is, I think, 2D. And then if you train on 3D, you have like 0.5% or 1.5%, they're like really data efficient. And our system is roughly equally data efficient as the symbolic methods, but designed for specific domains, or neuro-symbolic methods designed for specific domains. But, they're like one framework for all situations. And also, it's kind of comparable to the performance of end-to-end neural networks when you have 100% of data. Now, again, now goes back to Sohail's question. Yeah, slightly worse or comparable. It depends on how you, yeah. Okay. And it has similar levels of generalization. These are like different types of clever variants, and you can very quickly generalize to these new variants of clever on these kind of unseen complex reasoning problems. And we are on the left. And okay, so finally, I'm going to wrap up by saying there's the code part. And the code seems very important because people say, okay, all these things seems really hard to use. That is not the case. The thing is really simple to use. Okay, so here we have, as I said, the first order logic executor, which is pre-implemented and it's fully differentiable. There's no learnable parameters, so you just use them, right? You don't have to make any changes. What you need to do is, if you do 2D or whatever, you also have sample. We also have sample code for it. Then you can do 2D grounding and learning. Okay, what will be a sphere? Maybe that means you have an object detection network, or you have like some kind of clip features, encodings, and stuff like that. But here, this is the part that you can implement yourself, your own program, and you can go back and send them into our framework, which can be integrated so that you can run our framework on it. It is really simple. All you need to do is just to implement how you want to detect the sphere, right? You can use the clip features, you can use object detectors, you can do point cloud encodings if you're working on 3D point clouds. You can use pre-trained vision modules. You can use planners, if you want to have robotic manipulation stuff. Or you can have a constraint problem solver, right? So you can have all these things. And if the pre-trained models or whatever your implementation is differentiable, then yes, now the whole thing, because all these executions are differentiable too. So if your primitive executors, like finding a sphere is differentiable, then you can do fine tuning, right? You can fine tune and adapt your pre-trained sphere detector to a new domain, maybe different types of images, or you can train it from scratch. Let's say if you're training a 3D sphere detector on 3D point clouds, you can train it from scratch. If they're not differentiable, that is fine. You can still execute it. Then it becomes a kind of inference-only system that you no longer do some kind of the fine-tuning. But maybe you can say, okay, some predicates are not differentiable. The others are differentiable. And if the ones that differentiable are executed toward the end, then you can still, update them to the extent that they are differentiable. So really simple to use. And if, everything here is non-differentiable, everything here is just like pre-trained neural networks, like sphere detectors and left and relational detectors, then you can think about it as the whole system just reduced to the existing frameworks like HyperGPT, right? So or visual programming, right? So because if you don't do any fine tuning, you just take protein vision models and you just execute it, the NO or stuff like that, then the thing just really essentially becomes, Viper GPT, right? So it is sort of, you can argue, it's kind of a strictly a bit more flexible framework compared with existing inference only framework because it allows you to do fine tuning or tuning from scratch or integrate different kind of solvers if you want, although you don't have to. And code is again really simple to use, right? All these kind of short scripts are already provided, and everything here, executors are provided. What we need to do is just to implement your program about, let's say, how you want to detect a sphere. Okay, Joy really want me to say this because she wants to see more people using the framework, which I agree. Okay, so finally to wrap up, right? So the points to consider, I think there's this fundamental question about, how much do we learn and how much do we want to build in, right? It's the inductive bias question is a fundamental question. And people always say there's like bitter lessons or stuff like that. But I think we have to remember that there's nothing that is having like non-inductive bias, right? There's this no free lunch theorem, right? If you don't have any inductive biases, you learn nothing. So you have to have some inductive biases. I think historically it has been the case that minimal inductive bias is pretty powerful, right? If you have like convolution for, let's say, spatial correlation, right? If you have temporal recurrency, just using recurrency in, let's say, LSTMs or RNNs, this seems good. If you self-attention in transformers, this seems good, right? So I think these kind of inductive biases, although they're very minimal, they are inductive biases, but the level is pretty low, and having a kind of relatively minimal inductive biases will be great, which I think that is totally true. So now the question is, what are the minimal inductive biases we want to do or want to have if we're looking at a problem of, let's say, working across different domains, right? If you go to a new domain where you really have no data or very minimal data, and or getting more data is really expensive, let's say high energy fitness or something, then how can you really have a data efficient approach by having the right but also minimal inductive biases, and where do they come from, right? So I think in our case, if I'm giving a vision talk, I would say that is physics, and all you need to do is look into how light travels and stuff like that. But here, I would say what we're doing, the inductive biases we have is, or the very minimal logical reasoning, because the first order logic is kind of universal. It is not powerful enough. So there are questions that first order logic may not be able to represent, and these are maybe going back to Sohail's question about some kind of small number of them that is sort of capping our performance. But in general, I would say they're pretty universal and they're very minimal, right? So by having these kind of universal inductive biases, then it shouldn't hurt you from generalizing to new domains and treating them as a domain independent module. And then now you can learn domain specific part. So it will help your generalization, will give you much better data efficiency, and helps you to really generalize to new tasks and new domains and new modalities. And yeah, that's it. Thank you.
Yeah, thank you so much. Fantastic talk. I really enjoyed it. Maybe we have time for questions, a few questions. I just wanted to mention that this last part of the talk made me think like meta learning, these programs could also be an interesting thing, right? Like
Yeah.
yeah, potentially to
Yes.
make it as generalizable among. Have you looked into that direction more specifically?
Not yet. Yeah, but I agree. That sounds interesting. No, but we haven't looked at it. Yeah.
I see. I see. I see. Any other questions from the fellow panelists or from the audience?
I think there's one more. Small language models for PDE, a good approach. Can you be a bit more specific? Because it's uh, what do you mean by a small language model? In what sense for PDE? Yeah, we can wait a bit. I'm sure
Yep.
they're like typing or something. Yeah. Okay, there's a separate question. What do you think of GPT-01 for one? It can also do some learning on generative reasoning. In addition, how do you think of the future integrating symbolic neural learning? Would it be a future in this direction? Well, yeah, I think GPT-4, sorry, O one, GPT-01 seems great. Yeah, I mean, they are doing a lot of interesting, I think it is true that, if we look at what humans are, I think there's a fundamental question about whether a model is useful versus whether it is intelligent or whether it is solving or helping us to understand intelligence or whatever. I think O1 is incredibly useful. And I think think about it this way, right? So we may think humans are smart and we may feel like we do a lot of reasoning. Turn out to be not really the case. A lot of reasoning we do, a lot of plannings we do, like surprisingly short horizon. If we have a complex problems, we can't really think for like 20 different steps. We're not computers. So we just think about it as like 3 different steps and then we decompose them and then we recursively maybe decompose it a bit more. So the reasoning trace is surprisingly short even for humans. And that is the case that, I don't know how when I train O1, my guess is, maybe they have like these execution traces or reasoning traces, and then they just add it to their alignment module so that they train the model to do that. But anyway, so it turns out, if you think about it, if you have 20, if your execution trace is really long, then the number of possible combinations are exponential, right? So then it is impossible for a neural network to overfit to exponential data. But if your execution trace is relatively short, right? And so instead of mapping, input A to output B or X to Y, now you just map it to X from X to Y1, Y2, and Y3. And that still give you, much more, squared or cubed training data, but which is more harder to do, but sounds like doable. So in that sense, I feel like, they have been executing it pretty well and the model has been very useful. Although it hurts a little bit, I think, on the general recognition side, some kind of the things that for O are pretty good and O1 seems not very good, but O1 has its own strengths. So yes, in short, I thought they're great and seems like it's possible that you can scale up to some extent, and to the extent that it seems to be very useful for humans, right? So you may want to just use that in a lot of applications, and also, I'm sure things will get better, so it will be even more useful, and for more and more applications where having that will make sense in terms of from a business case, right? It will just generate enough values, and it will reduce the cost and stuff like that. But now there's this totally separate question about whether that is really answering intelligence or whether that is really doing you can say the ways humans do, or whether machine can really just produce things that are scientific findings or stuff like that. So that is a different question, because in a lot of applications you may want is like you have to have provable guarantees, right? About okay, whether this thing is provably correct. Let's say I'm flying a rocket or something, then or you definitely want to make sure that things are, you can prove that this thing also sort of makes sense. But I feel like that would be very hard for any of these foundation models, right? Just partially because they're trained to be progressive predictions, and it just seems impossible that all these models will be just like provably correct. So if you argue that if these models are really doing kind of smart, I would say intelligent calculations and reasoning, and actually reasoning in a way that eventually help us to understand science or or understand intelligence, that seems a stretch. So at least I feel like we don't have enough proof to say that right now. So that is my understanding. And there's, I think, a slightly second part of a question saying, how do you
Yeah.
think the future of symbolic integration in neural network will be promising to you? I thought yes, and definitely, but not for general applications like I have a live chat and they want to put a symbolic structure there. That doesn't make sense, because that's all about everyday conversations where you don't have to have that much reasoning. But if you look at specific domains like AI for science or something like that, then yeah, I think that's still very promising. Okay, sorry, I have a too long answer. I'm going back to the SLM thing. SLM email to clarify for the reference of using PDEs. Uh, for using PDEs for mapping weather input for causal reasoning for commodities
Yeah.
trading.
So maybe that one can be done offline. It
Yeah,
seems
that
like
seems really complicated, and you have a link. I cannot read a link right now. So why don't you email me? That's what it sounds like we're going to do anyway, and then I'll do that later. Um, okay, I'm going to mark this as live. And is it possible to use RL to make LLMs to write programs that are defined by humans? I think so. Yeah, in the case that there are a lot of people who are already doing that, that RHF and stuff like that. But you can just, instead of aligning with just like single value, you can align, and also I'm not sure if you even need RL, because if you already have a lot of programs that you can define the DSL, you can generate so many examples of it. You can just do fine tuning. And so definitely, and then also, in a lot of these cases, we do some kind of prompting, and as well, you can think about it as a little bit of, they're not really fine tuning, but you can do fine tuning too. Um, Okay, what can we do if the query itself lacks logic, is very fuzzy? Well, that is fine, right? Because, um, so first, what do you mean by a fuzzy question, right? It usually means that you just want, you know, at a very, very basic level, you know, it, it, if the thing is about visual reasoning, then at very minimal, you have to talk about and reason about something about an object. And if the thing or the scene, or let's say the scene in general, and if you can't really parse it into more, structured representations, which can be expressed by, let's say, first order logic, like iota or exist, or not or and all and stuff like that. Um, then it is fine. You can just, send it to and treat them as a parameter of reasoning about the scenes and seeing if the scene is satisfying certain predicate, and the predicate definition itself, or what is the attributes that you want a predicate to satisfy, can be very vague. That is fine. And then because then what you're going to do is, you're going to encode all the attributes or whatever as word embeddings and send it as a condition to your predicate verification network, right? So to our system, it is just like, okay, I just have a different conditioning. If I cannot really reason it to the step that I have like more logical operators, I just treat everything else as a conditioning, so that you can send it to the predicate network. So I don't think that would be a problem. If you have more specific examples, we can talk about it. Okay, finally, for temporal sequence reasoning and human action recognition data, was there any intuition on what part of the questions the model struggled with? For example, identifying a body part, or understanding what the prior conditions met, or their domain-specific quantities that were difficult for a framework. Well, unfortunately, for that work, that was like 2 years ago now, and I can't really remember these very specific difficulties for the models. But if that is a real question, like they say you use it in your framework and you want to use it, and there are specific things you look at. Again, I think I would say you can email me or the first author, and then we can talk about that. Because now I can't remember for that framework, well, that particular work, well, what is the difficult part for that framework? Okay,
Fantastic.
then.
Great. I think and we're right on time, a few minutes over, but that was great. I really appreciate your time, Jiajun. Thank you for the detailed answers. I think we all enjoyed both the talk and the Q&A. And I hope to see you in an upcoming conference. It's CVPR. It's going to be in Nashville, so we will definitely see you if you
Oh yeah, that would
attend.
be great. Yeah, definitely. I think I'll definitely be at CVPR. So I look forward to seeing you in person.